Okay, so today it's going to be a relatively light class because we don't have any derivation or anything of that kind. It's more like a seminar, so you can just relax and enjoy. Okay, so over the last few classes, we have studied essentially a phenomena that is beyond BCS theory, as I have emphasized many times, and that is phase fluctuations, which is not considered within BCS theory. So just let's start with the BCS theory itself. So in BCS theory, you know that you have these Cooper pairs that form, that pair of electrons that form a bound state on the Fermi surface. And when you have a Cooper pair, then all these Cooper pairs, since they are boson-like objects, they condense into a phase coherent state, and you know by now what this means. This is actually the order parameter of the superconductor. This is what we use in Ginsburg-Landau theory. Now, within BCS theory, of course, the superconductivity has a single energy scale, which is the superconducting energy gap, and Tc is therefore proportional to the superconducting energy gap. And when you increase, let's say, temperature, you have some of these pairs which get broken. How many of them will get broken? Of course, will be given by the Fermi-Dirac distribution. And because of this, we will have the superconducting gap, which itself gets normalized. So the superconducting gap decreases and it goes to zero exactly at Tc. So remember, within the BCS paradigm, the central thing of the BCS paradigm is that the gap disappears where the resistance appears. This is the central paradigm. All these other things, the shape of the superconducting gap as a function of temperature, this functional form, they could change if you tweak with the system a little bit. For example, if you take an anisotropic Fermi surface, that VKL that we take to be independent of K and L, if you don't take it to be independent of K and L, but you take some dependence of V on K minus L, all these features can slightly change. But the robust feature is what you observe here, and that is when the gap goes to zero, the resistance has to appear. Okay, so these I have, you know very well. Let me not go into it again. We had a complete tutorial on this, how to measure the superconducting density of states, and from the density of states, how to get the superconducting energy gap using tunneling. This has been covered. So let's go straight to the topic of today's discussion. So, you know that one of the major milestones in superconductivity was in the late 80s with the discovery of the superconducting cuprates. Now, why was this a major milestone? Because earlier superconductivity, let's say, from its discovery in 1911 to about 1986, so for about 70 years, 70 plus years, the superconducting transition, it increased gradually from 4 Kelvin and it went up to, let's say, 23 Kelvin or so. in the 60s, and then it remained saturated there for a very long time. And in fact, in those times, there were theoretical papers which suggested that superconductivity cannot exceed this limit of 23 Kelvin, using various kinds of arguments that we now know are not correct. Now, in 1986, two gentlemen, Bednorz and Müller, they discovered superconductivity in a class of materials that almost no one would have imagined can be superconducting. What were those materials? These were materials which were oxides and they were insulators. So the parent material that Bednorz and Müller worked with was lanthanum copper oxide, La2CuO4. Now, let me get my tab. Okay, so now La2CuO4, this material is this material. This is an insulator, and it's actually a Mott insulator. So I don't know how many of you here are familiar with Mott insulator. If you are not, then let me not get into Mott insulator right now. It's a more complicated object. But the parent material is an antiferromagnetic insulator. And then when Bednorz and Müller, they doped hole into it by replacing lanthanum by strontium or calcium. Then they got superconductivity in the material, and they got superconductivity at a temperature of 40 Kelvin, which was the record superconducting transition at that time. But even that was not dramatic enough, because within, let's say, weeks of this discovery, there were other groups who started synthesizing various other copper-based oxides with similar structure, and progressively the TC went high. So the one that you see here, Bismuth, strontium, calcium, copper oxide, this is called BISCO. This, in short, it's often called BISCO. And this superconductor has a transition temperature of 83 Kelvin, so about here. So these, then there are yttrium, barium, copper oxide, which has a TC of 90 Kelvin. That's the most popular one among this class of superconductors. There are also other superconductors in this category of copper oxides, which are mercury or thallium based, that have even higher transition temperature. Those are not that popular because mercury or thallium is quite poisonous, and therefore even synthesizing those material is not
Sir, why the transition temperature is increasing?
Why the transition temperature is increasing? Why the transition temperature is increasing is a very difficult question. So actually predicting the transition temperature of superconductors is very difficult. And as it turned out that high temperature superconductors, the physics is even more complicated and so far not completely resolved. What is known is that here, of course, you have the basic ingredient. There are electrons, and pairs of electrons form a bound state. That part is the same as any other superconductor. What is not
That
clear,
formula that is independent of the fact that whether it's a lower temperature superconductivity or higher temperature superconductivity.
yes, that is right. However, what is not clear in high temperature superconductors is what is the glue. So in conventional superconductor, we know that the glue is phonon, its lattice vibration. Here, there are plenty of evidence that the glue is very unlikely to be phonons. It is most likely not phonons. And since you have started with an antiferromagnetic insulator, here the likely glue is actually antiferromagnetic fluctuations. Even though by the time you dope it enough to become a superconductor, the antiferromagnetic long range order is lost, but the antiferromagnetic fluctuations persist. So these antiferromagnetic fluctuations are possibly the what acts as a glue. Even that per se doesn't explain to you why the transition temperature ought to be this high. And this is something that there is no consensus yet that has emerged. There are various fanciful theories like resonance, valence bond, and so on, but none of them really provide a cogent explanation of all the properties, including the high transition temperature. But nevertheless, don't mind the high transition temperature. It's good that you have a high transition temperature. Beyond that, as far as we are concerned, the puzzle that these materials posed to us was something else. So these materials, as I said, they posed several puzzles, including what the glue is. But then the relevant puzzle for us is this phenomena which is called the pseudo gap. So this is the superconducting transition temperature, as I said, 83 Kelvin, it's around here. But you see that even at the superconducting transition, you have a significant gap in the tunneling spectrum. So here this is, for clarity, each of the tunneling spectrum is actually shifted up by some amount. Otherwise, this normal state value for all of them would have been the same, but then it would have become difficult to see. At 84 Kelvin, which is already 1 Kelvin above TC, the superconducting gap has not closed. But the point is that it doesn't close even up to, let's say, 123 Kelvin, it's still there. And if you sort of look very carefully, it's there maybe even up to 160 Kelvin or so. This is the death knell to the BCS theory. BCS theory cannot explain such sacrilege. The superconducting gap, which continues to persist above TC, is just not possible within BCS theory. So that got people thinking that I have started with a doped Mott antiferromagnetic insulator, and then I have doped holes into it and gotten this superconductor. Now, since I am doping holes here, starting from something that was an insulator, the superfluid density is quite low for two reasons. One reason is that I am doping a small amount of carrier, and then the second reason is that when I dope a system, I also introduce a lot of disorder, and when you know that when I introduce disorder, the superfluid density reduces. So the superfluid density is low. That is also supported from penetration depth measurement, which observed a large penetration depth. So then in a very powerful and influential paper, this is a paper which I want all of you to read, because it's a paper that I'm sure all of you can just open this paper, read it and understand it, including all the calculations that is there inside. So it's a paper that has very interesting calculations, but at a very elementary level. So you can sometimes see how great work comes from seemingly extremely simple idea. Because once you read the paper, you might wonder why you haven't written the paper instead of these two guys. So what they said is that since we have the gap that is not closing at Tc, possibly the superconducting gap in this material is an irrelevant energy scale as far as the transition temperature is concerned. In which case, there has to be some other energy scale which is much lower than the gap and which is determining Tc. And that is when these two gentlemen started exploring the superfluid stiffness, which of course the concept of superfluid stiffness already existed as a theoretical construct. But they started looking at it critically in various superconductors. No one really bothered to calculate this and find out whether this could be of any relevance. It was just assumed not to be relevant. Sometimes such assumptions continue for several decades before its question, and this is one such example. Okay, so by now you know very well what the superfluid stiffness is and how we define it. It's the energy cost of providing a unit twist over a unit length, which is nothing but grad of theta. So grad of theta mod square. So this superfluid stiffness, you know that it is given by this quantity here, and this A, this characteristic length scale. If you take, let's say, thin films, then it is the lower between the coherence length and the thickness D. Yeah. Okay, this is a calculation I have told you to do. I don't know whether you have done it or not. But if you do this calculation, take clean lead or clean niobium tin and you calculate the superfluid stiffness from this formula. It's very easy because you know the coherence length, you know the penetration depth, and then rest are all universal constant, plug it in, and in fact this superfluid stiffness doesn't even depend on the effective mass, which is a good thing about superfluid stiffness. So therefore, the effective mass also doesn't skew your actual value. You have the effective mass here, but you also have the effective mass embedded in NS, so therefore it drops out. All right, and instead of A, you put the coherence length, you know the penetration depth, and calculate. When you calculate, you get this J to be a ridiculously large number. So lead, it is 10 to the power 5 Kelvin. Niobium 13, it's 10 to the power 4 Kelvin. Okay, sometimes it may be even a little lower, few hundred Kelvin, but doesn't matter. It's just far too large to be of any significance. So you will not excite this fluctuation because the energy cost is so much higher compared to Tc, which is the maximum temperature up to which superconductivity survives. But now you in the if you do okay, I don't have the okay. Now let me, on the other hand, I have to open now something and show you a table. Let us do this calculation for other things. All right, where is my table? Yeah, okay. You can see a table here. Are you able to see a table? Am I sharing the
Yes,
right
sir. Yes, sir.
page? Yeah, okay.
Mm.
Yes,
So you
sir.
can see here now these values of J, the superfluid stiffness. As expected for all these elements, it's very large and it does not matter. But let's come to high TC cuprates. Disco, the sample that I showed you. Here the superfluid stiffness is about 77 Kelvin. Okay, that is very close to the TC of 84 Kelvin. So here the phase stiffness is not very large. Phase fluctuation will of course play a role. You come to other things. Lanthanum strontium copper oxide. This is the compound in which Bednorz and Müller had discovered their superconductivity. So lanthanum strontium copper oxide, here it is about 40 Kelvin and Tc is also about 38 Kelvin or so. So if I take J by Tc, here it's of the order of 1.2. So these are all of the order of 1, 1.2, less than 1, which means that for these compounds, you have the phase fluctuation that can play a very important role. All right. So let's get back to our presentation. Okay. All right. So this is when the superfluid stiffness J is smaller than the superconducting gap, then of course the superconductivity will be destroyed. The zero resistance state will be destroyed by phase fluctuation as soon as my temperature is of the order of J. So therefore Tc will be roughly of the order of J by Kb. However, the, even if the phase has got scrambled, so all these pairs which were forming the Cooper pairs, all these paired objects, even if they become phase incoherent, they can still exist as pair. And the binding energy of the pair, that is the gap. So therefore, these pairs as an entity will keep existing up to a temperature which is delta by Kb. And now delta by Kb is a temperature that is larger than Tc. So we call that T star. So now what will happen is that your superconductivity will get destroyed by phase fluctuation at this temperature, but your superconducting gap, which actually is a signature that you have this pairing, that will not close. That will persist up to a much higher temperature, and this is what was mooted as the explanation for the pseudo gap state that you see above Tc. All right. So between Tc and this temperature T star, you have this phase incoherent Cooper pair, and that is what gives you the pseudo gap state. This was thought to be the explanation in these high Tc cuprates because of what I already said, the low superfluid density and the large penetration depth, which is essentially identical. Now you know that the superfluid density can also reduce in a conventional superconductor. I don't need to go to high TC cuprates. I can just remain with conventional superconductors And there also I can introduce disorder, and when I put in disorder, my superfluid density will decrease. This is something that we have explicitly derived, and we will outline the derivation again here. Now, okay, so let me skip that part. Let me go straight here. So this is the argument that we have already studied in great detail. You know that this is the real part of the conductivity. This tau is the scattering time. So Vf into tau is the mean free path, and delta is the superconducting gap. So delta by h cat is the characteristic frequency scale at which my Cooper pairs will dissociate. You also know that you have this sum rule here, and this sum rule is valid at any temperature. So if you are in the clean limit, all these electrons go into the superfluid state and they contribute to this delta function peak here. However, if you are in the other limit, this is the clean limit. If I am in the other limit, the dirty limit, then this tau is very small because my mean free path is short. So there it will be the opposite. My delta is here and 1 by 2 pi by tau is here. So now when I go below Tc, what will happen is that only this part of the spectral weight will go into the condensate. That will give me the superfluid fraction, and the remaining part will not. And this we have derived that Ns by N, N is the total carrier density, Ns by N in this case is proportional to tau into delta, because it's proportional to this area here. So tau into delta, actually the tau comes from this tau and the delta comes from this delta. And then the remaining are the proportionality constant that come in, and therefore this ratio is 4 tau delta by h cross pi. And this for a dirty superconductor is much less than 1. And if I start making these larger and larger, I am distributing this frequency, I am distributing all the electrons over a larger frequency range. The spectral weight is distributed over larger frequency range, and the amplitude of the normal state, so this value comes down, which means that Ns by N becomes progressively smaller. So therefore, now since J is directly proportional to Ns, this means that at some point, if I keep on putting disorder, then I can drive the J to be very, very small, provided by that time delta also does not decrease. Now we know that from Anderson theorem that delta is not strongly affected by disorder. It's not an exact statement. Delta actually decreases with disorder, but it does not decrease to zero. At strong disorder, you can see that the delta goes somewhat towards a saturation value. So now let me see. So now let us see what's the manifestation of this. So just to give you a perspective, if I take, let's say, a superconductor, which is niobium nitride, it's quite a high temperature in the sense that among conventional superconductors, it has a Tc of 16 Kelvin, which is not very small. But what is the Ns by N? If you calculate the Ns by N, it's 0.001. So you can understand that it's in a very dirty limit. Actually, most of the superconductors that we deal with are in the dirty limit, where you have this 2 pi by tau, which is much larger than delta by h cross. It's very difficult to get superconductors which are in the other limit. All right. So, okay. So now this, what I am showing you here, all these ideas were developing from from mid 90s onward, but there was a group of three people, and this is a very celebrated paper by these three gentlemen. When they did this paper, they were all people at TIFR. Now Mohit Randaria and Nandini Trivedi have both relocated to Ohio State University now for more than a decade. Amit Ghoshal, who was a student at that time, is now a faculty in ISER Kolkata. So these three people, what they did is that they put the whole thing into perspective. How did they put it into perspective? Of course, when I say perspective, it is theoretical perspective. So they said that, okay, we know what phase fluctuation does. We have a qualitative idea that when J is smaller than delta, I will have phase fluctuation which will dominate and so on. But instead of just so many ideas which one has to absorb, let's calculate. So let's calculate within a very simple toy model. And they took this toy model, which is a minimal model for a superconductor. So if you remove this, then it's a minimal model for a superconductor, and they added this to have a minimal model for a disordered superconductor. So what is this model? You can see this first term is the kinetic energy, destroying an electron at site I and creating at site J. So that means that the electron is hopping by one side. Now it hops by one side, another side, another side, another side. So this is writing the Hamiltonian in real space. This becomes a kinetic energy term. So this makes the electron hop from side to side. In the K space, this is the same term that we write as Ck dagger Ck. Then what we assume is that if you have electrons with up and down spin on the same side, they have an attractive interaction. This is to simulate the attractive interaction. And therefore, you put a negative energy for two electrons with opposite spin on the same side. So this is the attractive pairing interaction. And now what they did, so this is called the attractive Hubbard model, and this is known for a long time. This is not a discovery of these people. What these people did is that with that they added, you know that you have to work in the grand canonical ensemble, so you need to put a chemical potential here. What they did in addition, they put this Vi, which is a random disorder potential. So at every point, my chemical potential is slightly different. That is how I am putting in disorder. So whenever I am putting in disorder, locally I am changing the chemical potential a little bit. So that's a very elegant way to put in disorder. And then what they did is something that you guys know. They solved this using Bogoliubov-Deugen approximation. The Bogoliubov-Deugen equation that you have all derived, they just rehash this problem on the Bogoliubov-Deugen formalism and solved it on a computer. Because Bogoliubov-Deugen is the equivalent of Schrodinger equation. You can solve it in real space. And what did they get? So what they get is this that you see here. They say this V is my disorder potential and this is the kinetic energy. So the effective disorder is disorder by kinetic energy, V by T. So 0 means perfectly clean and very high V by T means very disorder. So I'm starting with 0 disorder and going to more and more disorder. First, let us look at the gap. Just like Anderson said, the gap is not very strongly affected by disorder. Okay, it decreases a little bit, then increases a little bit, but more or less it remains finite everywhere. Now you calculate the superfluid stiffness, J, and this is how J varies. At low disorder, J is much larger than delta. So therefore, it's an irrelevant energy scale. We will not excite too much of phase fluctuations. But then as you increase disorder, J decreases, crosses over and becomes smaller than delta. This is where, if you did an experiment, so PC initially would be determined by delta. This is the BCS region. And then we will smoothly go over to the phase fluctuation region. So here TC will be determined by J. So TC will continuously keep falling like this, even though delta remains more or less finite. So this is where, now you know that these are energy scales, but energy scales divided by KB roughly will give you the characteristic temperature. So this is where you see a pseudo gap. If you stay at, let's say, this disorder and do an experiment as a function of temperature, you will see that at this temperature, my superconductivity is destroyed, but gap remains, continues to remain and get destroyed at a much higher temperature. So these concepts, Ghoshal, Randeria and Trivedi, they proposed in 98, and then in 2001 in a more elaborate paper they expounded this concept in more detail. But at the time when they gave this concept, pseudogap was observed only in high temperature cuprates. Now, how the high temperature cuprates, unfortunately, are very complicated objects. So there was this proposition, as I said, that pseudogap is from phase fluctuation. But since the parent material is an antiferromagnet, there are also many other propositions for pseudogap, which are based on competing orders. So some people say that no, superconducting gap actually disappears there. The gap that is emerging above PC is coming from a different order, like charge density wave, which also creates a gap. So you needed, on the other hand, these simulation of Ghoshal, Randeria, Trivedi, this was so general that if correct, it should not need a complicated system. You should be able to take any simple superconductor, and if you disorder and reduce the superfluid density, at some point you should see a pseudo gap. So these experiments actually came up in 2010 and 2011 by actually simultaneously by 3 groups. One of them was, actually 2 of the work were by the same first author, Sassepe, who is a French physicist, and one of them, which was on niobium nitride, this was by, in our group, by Mintu Mondol. So Mintu Mondol is a former student who is now a faculty in Indian Association for the Cultivation of Science. Okay, so I will show you now some data on our work, because that is for which I have the data handy with me. So you have this niobium nitride, and here you can increase disorder. So niobium nitride is very simple crystal structure. It has a crystal structure of sodium chloride, your common salt. And what you can do is you can have more and more vacancies in the niobium nitride crystal structure. They act as scattering centers, reduce the mean-free path, so that's a way to increase the defect. So you increase the defect, and you see that Tc gradually is decreasing. The Tc is gradually decreasing as you have more and more of disorder. Your normal state resistivity is increasing as expected. Tc decreases, and then at some point Tc becomes too low to measure. So it becomes less than, for our lab, the lowest temperature that we can measure is 0.3 Kelvin, 300 millikelvin. So it becomes lower than that. But now you take, let's say, one of these superconductors, something which has a Tc of somewhere here, 2.7 K, and you measure the superconducting gap. So what I am showing you here is the same spectrum that you see for a superconductor, but this is color coded. So the color, the intensity of the color corresponds to the conductance. The y-axis corresponds to the bias voltage, and here the x-axis is the temperature. So you have many spectrum at different temperature that are encoded in this color plot. So this blue is the superconducting gap, because blue is the low conductance region. So that is the superconducting gap. Red is roughly the normal state conductance, which you will see either at high bias or at high temperature. Now you can see the superconducting gap, it vanishes close to about, let's say, maybe 7 Kelvin or so. It becomes very faint there. But now you can also measure the resistance as a function of temperature. And if I put that on the same curve, on the same plot, the Tc is here. So you have the Tc, which is 2.9 Kelvin, and T star, which is 7.2 Kelvin. Now niobium nitride is a superconductor that doesn't have any of the complications. It doesn't have any magnetic ground state, any additional complicacy that the high temperature superconductor has. So this was one of the early validation that indeed phase fluctuation can destroy superconductivity and produce a pseudo gap state. However, you need a more direct proof, and for a more direct proof, you have to compare J and delta. So this is what we saw initially, is that when you make more and more disorder, so here the measure of disorder is actually the mean tree part divided by the de Broglie wavelength of the electron. The de Broglie wavelength of the electron is actually proportional, is inversely proportional to Kf. So you can see as you go to more and more disorder, Tc gradually decreases and eventually becomes lower than 300 millikelvin. But your superconducting gap, which is this blue, that initially T star is the same as Tc. So superconducting gap vanishes at Tc, but when you go to strong disorder, low superfluid stiffness, the gap vanishes roughly at the same temperature, which is close to 6 to 7 Kelvin, but the Tc comes down, so you get this pseudo gap state here. All right, now you can, for all these films, you can calculate. You have measured the superconducting gap from STM, and this is the Tc of the film, the superconducting transition temperature. So I am plotting here. This green one is the superconducting gap for these films with different Tc. This blue one is the penetration depth that is measured for all these films, and this is the penetration depth so the penetration depth at very low temperature. So this is lambda 0, and then using this lambda 0, the coherence length that you calculate from the upper critical field, you can get J. And you see for the clean limit, for, or not the clean limit, the cleaner sample, which has a TC of 16 Kelvin, J is much larger than delta. But as you go to more and more disordered sample, this J comes down and at some point becomes even smaller than delta. And this region where, this region on this side of this dashed purple line is where you see the pseudo gap. So you actually see the pseudo gap where your J is smaller than delta. So this is actually, this is what shows you that the pseudo gap is actually resulting from phase fluctuation destroying the superconductivity. All right, these are some images of the pseudo gap for the other two reports that appeared simultaneously that I mentioned to you at the beginning. And okay, and I think this is all that I had to show you. Then we have studied many other systems, and other people have also studied different systems. So this is, for example, the data on another compound, another superconductor, which is molybdenum germanium. And here again, for a molybdenum germanium, you go to lower and lower thickness, and at very low thickness, you start seeing this pseudo gap appearing. So this is for a thickness of 2 nanometer, you have a pronounced pseudo gap that has appeared. And whenever you have this pseudo gap that has appeared, you can go back, look at the penetration depth, how it looks like. So you see this penetration depth, this is for this sample which has the pseudo gap. You can see that it has, there is somewhere where the 1 by lambda square, the superfluid density is flat, then it varies linearly with temperature, and then close to TC it crashes very rapidly. And again here you can see that for the sample where you see this pseudo gap, the J has become of the order of delta. All right, so I think I will stop here. This is what I wanted to show you, and any questions? Okay, so if there are no questions, first let me say that for I think there are 2 or 3 non-TFR students who are still submitting the assignments dutifully. So assignment 6 and assignment 7 for them is corrected and is on the same Google Drive link. The second thing is that what we will start next is Kosterlitz-Thouless transition, which is the other kind of phase fluctuation phenomena that one sees primarily in thin films. Now, many of you have mentioned that Friday you have some exam on Saturday, and Friday is inconvenient. Is that right?
Yes, sir.
Yes, sir.
Okay. So in that case, so Wednesday I have something already planned. So what we will do is I will give you the assignments this week, and then the next task, let's have it directly on Monday, because the Kosterlitz-Thouless, once we take it, we will have it more or less continuously. It's no point starting it just before an exam where you will not be able to concentrate much on it. So next class again on Monday. In the meantime, if any of you want to discuss anything about the video project, as usual, fix a time and then we'll meet at that time and discuss. All right. See you next.